Welcome friends. In this video we will be looking at Stokes theorem. Stokes theorem is actually a generalization of Green's theorem to three dimensions. First of all, we will have to look at the orientation of surfaces in this scenario. So we will basically be dealing with integrals over surfaces which have either the upward orientation or the downward orientation as shown in these figures. So suppose if we are having a surface which is having an upward orientation like this and whose boundary is a closed curve like this. So we will be integrating over surfaces which have an upward or a downward orientation and whose boundary is a closed curve. So you can see here, this is the closed curve that I am talking about. Now we will say that we will have a positive direction in C. So we will have to first identify the direction of orientation of C. That is, it will have either the positive orientation or the negative orientation. So to identify the direction of orientation of C, what we will do is, suppose we are having an upward orientation, then we will consider a person walking with his head in the direction of orientation of the surface. Okay, so this is having an upward orientation, so this person is walking with his or her head in the direction of orientation of the surface. And suppose while walking, she is walking like this. Okay, and suppose while walking, if the surface is on her left, then we say that she is having a positive direction. She is walking in the positive direction of C. So now you can see she is walking in this direction, her head is in the direction of orientation of the surface sigma, and hence this is the positive orientation of C, or this is the orientation of C that we will be considering. Now suppose if she was walking in the opposite direction, suppose she was walking like this, and but still her head is in the direction of the orientation of the surface, but what happens is this surface is on her right, this surface is on her right, so we will say that she is walking in the negative direction. So she is walking in the negative direction. The actual direction of C is this one. She's now walking in the negative direction. We can find out the direction of C using our thumb also. So what we have to do is we have to curl our thumb fingers in the direction of if we curl the fingers in the direction or in the orientation of C. See, for example, here the direction of C is like this. So we have curled the fingers. The fingers are in the direction of C. Then the direction of thumb will be in the orientation of the surface sigma. Okay, so you see, if the thumb is in this orientation, and suppose if our fingers are in this given orientation, then we say that we are having a positive direction of C with respect to that given surface. So that is how we will be identifying the direction of C using the thumb rule. Okay, I'll repeat once again using the thumb rule. That is, here you can see in this given figure, the fingers other than the thumb finger are directed in this direction. Okay, and your thumb finger is in the upper direction. So if this is the orientation of sigma, then this will be the direction of C. Okay, on the contrary, if your surface is oriented downward, then you see if you keep your hand like this, see your thumb finger is pointing downwards and your fingers are in this direction. So this is the positive direction of the curve C. So here you can see, so in short I will just sum it up like this. So if this is the curve C, if the curve C is in this direction, that means this surface sigma will be oriented up. So if the sigma is oriented like this, then this should be the direction of C. This should be the positive direction of C. And if your sigma is oriented downward like this, then this should be the orientation of the curve C. You can use either the thumb rule like this. So this thumb is facing down and the fingers are facing in the orientation of C. So thumb is facing in the direction of orientation of sigma, and the fingers are facing in the positive direction of C. Here also the thumb is facing in the direction of orientation of sigma and the fingers are facing in the positive direction of C. Or you can consider this walking example where a person is walking with his or her head in the orientation of the surface sigma. Then if the surface is on her left, then we say that she is walking in the positive direction of C. And if her head is in the direction of orientation of sigma, but she is walking like this and the surface is suppose on the right of towards the right of her, then we say that that is she's walking with her head in the direction of sigma, but the surface is to her right. Then we say that she's walking in the negative orientation of C. This will be clear when we are dealing with some problems. You can see now what we will consider one more example here. See, this is the thumb rule that I was talking about. These fingers are actually directed in the positive direction of C. This thumb is directed in the orientation of sigma. Okay, so that is the connection between the orientation of sigma and the positive direction of C. So if you are holding your fingers in the orientation of C, then your thumb will give you the orientation of sigma. Okay, then your thumb will give you the orientation of sigma. I'll repeat once again. If your four fingers are facing in the direction of C, in the positive direction of C, then your thumb will give you the direction of sigma if you have kept your hand like this. Okay, now moving on to the Stokes theorem. Stokes theorem. So before that, we will just recap how to evaluate curl F. You see, curl F can be evaluated like this. You can use this formula instead of this direct formula. That is, you write it in the determinant notation. The first row is ijk, second row is dou by dou x, dou by dou y, dou by dou z, and the third row is fgh, where fgh are the components of the vector field. So your vector field is fi plus gj plus hk. Okay, so if sigma is a piecewise smooth surface and suppose C is its boundary, which is a simple closed piecewise smooth curve, then and if F is the vector field given by Fi plus Gj plus Hk, then the work done is actually given by this integral is actually the work integral, where T is the tangential component, S is the arc length parameterization. So work done is given like this: integral over Cf dot TDS, which is equal to double integral over sigma curl F dot NDS. So we can use this as a formula for work done. So in other words, this is an alternative form of the same theorem. So the work done, that is integral over Cf dot dr, can be written as double integral over sigma curl F dot NDS using the Stokes theorem, where sigma is the surface along which we are calculating, across which we are calculating the work done, and C will be in the positive orientation. Okay, so to sum it up, the work performed by a force field on a particle that traverses on a simple closed piecewise smooth curve C in the positive direction can be obtained by integrating the normal component of the curve over an oriented surface sigma bounded by C. So we will repeat once again. Work done. The usual formula that you have studied is integral over C F dot dr is equal to double integral over sigma curl F dot n ds, where n is the normal component. Okay. Now I'll illustrate all of these topics using this given example here. So you look at this question. Find the work performed by the force field F is equal to x square I. You write it down. F is equal to x square I plus 4x into y cube j plus 4x into y cube j plus y square xk plus y square xk. So you have x square I plus 4x into y cube j plus y square into x k on a particle that traverses the rectangle C in the plane z equal to y. So this is the plane z equal to y as shown in this figure. So this is the plane, or this is the surface along which we have to integrate. Now you see this direction of C is given like this. This is the direction of C. So suppose if a person was walking like this in the direction of C, then what happens if a person is walking like this, then the surface is to the person's right. So this is the negative orientation. This is the negative orientation. On the contrary, suppose if a person was walking like this, then what happens? This is the direction of C and the surface is to the left. So this is the positive orientation. So that means that is the orientation, not the negative or positive. That is the orientation of the curve sigma. This is the positive orientation of C. Now once again, if you are using the thumb rule, then you fold your four fingers in the direction of motion. Okay, so what happens is you're folding your fingers like this, then your thumb will be in this direction. So that means this, what happens, this is the, so what happens, just I'm sorry, when you're folding your fingers in the direction, so what happened, you have to, I'll draw it correctly. So your fingers will be like this, 1 2 3 4, and this will be the direction of your thumb finger. So this is how you will have to consider if you are using the thumb rule. So your direction of C is like this. So if you are folding your four fingers like this, then this is will be the direction of the thumb finger. Okay, so this is the orientation of sigma. Orientation of sigma is downward. It will be clear when you are using your hand rather than when I'm trying to draw it like this. Okay, so this is the orientation of sigma and C. So once again, I'll just sum it up. Your direction of C is like this, so hence this will be the orientation of sigma and this will be the direction of C. Okay, now we will first evaluate curl F for this given question. So curl F, curl F, curl F is equal to I j k dou by dou x dou by dou y dou by dou z x square 4xy cube y square x. These are your components f, g, h respectively. Now evaluate this determinant. So you'll be having this is equal to I into dou by dou y of y square x minus dou by dou z of 4x y cube. So what is dou by dou y of y square x? That is 2xy minus dou by dou z of 4xy cube is 0 minus j into dou by dou x of y square x minus dou by dou z of x square. So what is dou by dou x of y square x? That is y square minus dou by dou z of x square is 0 plus k into, you'll be having dou by dou x of 4xy cube minus dou by dou y of x square. So dou by dou x of 4xy cube is 4y cube minus dou by dou y of x square is 0. So this is equal to 2xyi minus y square j plus 4y cube into k. Okay, so using the Stokes theorem, work done is equal to double integral over sigma curl f dot n ds. Okay, now that is equal to double integral over sigma 2x y I cap minus y square into j cap plus 4y cube into k cap. Now since your orientation of surface is downward, you see the direction of C is given like this, so the orientation of the surface is downward. So what will happen is your n cap will be dou z by dou xi plus dou z by dou y j minus k. As you can see here, it is dou z by dou I plus dou z by dou y j minus k. So we will write it here, dou z by dou xi plus dou z by dou y j minus k. This you would have studied when when you were dealing with flux integrals. Into, you will be having dA. Now we have to find out dou z by dou x, dou z by dou y, and things like that. So what is your z? Z is equal to y. So if z equal to y, so z equal to y, that implies dou z by dou x is equal to 0 and dou z by dou y equal to 1. So you'll be having this is equal to double integral over sigma 2xyi minus y square j plus 4y cube k dot product with, this is dot product, okay, dot product with, you're having, so just make sure you write the dot product there. So 0I plus 1j minus k dA. This is equal to double integral over c. So you rewrite it like that, integral over sigma, you rewrite it as integral over c. Now we have converted it into c, or not c, integral over sigma, when we have to take the projection onto the surface. So double integral over r, you change it as double integral over r. What is r? R is the projection. Okay, so we have double integral over r, 2xy into 0 is 0, minus y square into j is minus y square, plus 4y cube into minus 1 is minus 4y cube. Then you are having dA. Now we will consider this projection onto the surface R. Okay, so what is projection onto the surface R? So what is its projection now? Now when you are considering the projection, this is your projection R. Okay, this is your projection R. So the projection is x coordinate is 1, y coordinate is 3. So this is 3. This is your region R over which you have to integrate. So x varies between 0 to 1, y varies between 0 to 3. So this is equal to x equal to 0 to 1, y equal to 0 to 3. Negative sign I'll keep it outside. Y square plus 4 into y cube, right? dy dx, y square plus 4 into y cube dy dx. So that is equal to, negative sign I'm keeping it there. Then you are having integral x from 0 to 1, y cube by 3 plus 4 into y raised to 4 by 4 within the limits 0 to 3. Okay, y equal to 0 to 3 dx. So that is, you will be having, that is equal to negative x equal to 0 to 1. Here 3 cube, 1 3 will get cancelled, so we are having 9 plus 4 is getting cancelled. This is 81, 9 plus 81 times dx. That is 81 plus 9 is 90, negative 90 into x within the limits 0 to 1. So the final answer is minus 90. Minus 90 is the final answer. So the work done along the surface or across the surface is equal to minus 90. Now we will move on to the second question. Here, verify Stokes' theorem for the vector field f is equal to 2zi plus 3xj plus 5yk. So the force field is f is equal to 2zi plus 3xj plus 5yk taking sigma to be the portion of the paraboloid z equal to 4 minus x square minus y square. Z equal to 4 minus x square minus y square. for which z is greater than or equal to 0 with upward orientation and c to be the positively oriented curve x square plus y square equal to 4 that forms the boundary of sigma in the xy plane. So the figure is drawn here. So your surface is actually a paraboloid like this. You can see this is the paraboloid. It is going on like this, but for z greater than 0. That's why we are not considering the negative part. Okay, for a negative part of z. And then you have with upward orientation. So the orientation is given to be upward, where c is the positively oriented circle x square plus y square equal to 4. So you see, when a person is walking like this and with his or her head in the direction of orientation of sigma, the surface is to the person's left. So this is the positive orientation. So this is the positive orientation. Or in other words, when you are keeping your fingers like this, you see, when you are folding your fingers in the orientation of the uh, in the positive orientation of C, then your thumb finger will actually be like this. So you see, your orientation of C is like this. You fold your fingers in the direction of that orientation, then your thumb finger is like this. Or in simple terms, since C is in this orientation, sigma is upward, so this is the orientation of sigma and this is the positive orientation of C. Okay, so I hope the orientation part is clear. Now we will find out what they have asked you to verify Stokes theorem. So that is very important. They have asked you to verify Stokes theorem. So what you have to do is you have to first write down w equal to integral over c f dot dr. This is equal to double integral over sigma curl f dot n d S, or here it is dA. So what happens is you have to first verify this LHS using the usual methods that you have studied. Then you have to show that it is equal to RHS using the Stokes theorem. Okay, so first we will evaluate the left hand side. So for evaluating the left hand side, we will take the surface, that is the curve C is the circle x square plus y square equal to, what was the radius, x square plus y square equal to 4, x square plus y square equal to 4 in the anticlockwise direction. That is the this given circle. You can see here, this I have drawn the projection of the surface on the xy plane. The projection of the surface on the xy plane is like this. Okay, so I have drawn that there. So first we will evaluate the left hand side. So evaluating left hand side, so here x equal to r cos theta, so 2 cos theta, x square plus y square equal to r square, y equal to r sin theta, so 2 sin theta. Now you have dx and you have to evaluate the work done. So w equal to integral over c f dot dr. Okay, f dot dr. Now the z component here is 0. That also you write it down. So this is equal to integral over c. You are having 2zi. So f dx is 2z into dx plus g dy. So this is your fgh respectively, fgh. Okay, so you have 2z dx plus 3x dy plus 5y dz. Okay, 5y dz. Now z is equal to 0. The z component is equal to 0. So what you have is, this is equal to integral, see, this direct angle of theta, or if I am writing it in terms of t will be between 0 and 2 pi. So I can write it as 0 to 2 pi. The limits of t is 0 to 2 pi. Here you have z equal to 0. So this first component will be 0. Okay. Plus, now you have 3 into x. So 3 into x is 2 cos t. So 3 into 2 cos t. Now y is equal to 2 sin t. So dy I can write it as 2 into cos t dt, and here z equal to 0, so dz is also 0. Okay, so you have that part also as 0. So your final answer will be something like this: 3 into x is 2 cos t dy. Yes, so you'll be having the final integral as the final integral is equal to integral 0 to 2 pi 4 3s are 12 into cos square t dt. So that is equal to 12 into 1 plus cos 2t by 2 within the limits 0 to 2 pi. So you can write it, that is equal to 6 times theta within the limit 0 to 2 pi. I'm sorry, here I've not integrated it. So this is equal to 12 into 1 plus cos 2t by 2 integral 0 to 2 pi dt. That is equal to 6 into theta within the limits 0 to 2 pi plus sine 2t by 2 within the limits 0 to 2 pi. So that part is 0. So you'll be having 6 into 2 pi, which is equal to 12 times pi. So that is the final answer here, 12 times pi. So we have evaluated the left hand side using the direct integration method, that is integral over c f dot dr. We have integrated it as a line integral. Now the right hand side, that is double integral over sigma curl f dot nds, that we will evaluate using the Stokes theorem. Okay, so right hand side, for that what we need is we will have to first evaluate curl f. So we will evaluate curl f first. Okay, we will evaluate curl f first. So what is curl f is equal to curl f is equal to I j k dou by dou x dou by dou y dou by dou z. Then you have 2z 3x 5y. So curl f is equal to I into, that is equal to I into dou by dou y of 5y minus dou by dou z of 3x. So dou by dou y of 5y is equal to 5 minus dou by dou z of 3x is 0 minus j into, you will be having dou by dou x of 5y minus dou by dou z of 2z. Okay, so dou by dou x of 5y is equal to 0 minus dou by dou z of 2z is equal to 2 plus k cap into, you will be having dou by dou x of 3z minus dou by dou y of 2z. 3 dou by dou x of 3x minus dou by dou y of 2z. So you will be having dou by dou x of 3x is 3 minus dou by dou y of 2z is 0. So the curl f is equal to 5i plus 2j plus 3k. Okay, and we will now evaluate dou z by dou x and dou z by dou y from this. So dou z by dou x is equal to minus 2x, dou z by dou y is equal to minus 2y. Now we know work done according to the Stokes theorem is equal to double integral over sigma curl f dot n ds. Now since n is in the, since your surface is oriented upward, n will be equal to curl f dot minus dou z by dou x I minus dou z by dou y j plus k, then you will be having dA. Okay, this I can write it as r, double integral over r, which is the projection onto the xy plane. Now you substitute curl f and all these things, that is equal to double integral over r. Curl f is 5i plus 2j plus 3k dot product with 2x plus 2y plus k, 2x plus 2y plus k dA. Okay, k dA. So that is equal to, you'll be having double integral over r 5 into 10x plus 2 into 2 4y plus 3 dA. Now let's take the projection. Projection is the circle with radius 2, x square plus y square equal to 4. So writing it down in polar coordinates, theta is equal to 0 to 2 pi. The projection is circle with radius 2, right? Yes, projection is circle with radius 2. So r equal to 0 to 2, 10 into x equal to r cos theta, y equal to r sin theta or sin t, and t varies between 0 to 2 pi. Okay, and those limits we have already written. So r equal to 0 to 10 into r cos t plus 4 into r sin t plus 3 times r dr d theta, r dr d theta, r dr d theta, r dr d theta. Okay, so this is equal to theta from 0 to 2 pi. You are having 10 into an r equal to 0 to 2, 10 into r square into cos theta. Okay, we will use the variable theta, so cos theta plus 4 into r square into sin theta plus 3r, then you are having dr d theta. So here we will use the variable theta instead. So theta equal to 0 to 2 pi, then you are having 10 into r cube by 3 within the limits 0 to 2, then you are having cos theta plus 4 into r cube by 3 within the limits 0 to 2 sin theta plus 3 into r square by 2 within the limits 0 to 2, then finally you are having d theta. So let's simplify this. We will be having this is equal to theta from 0 to 2 pi, then you will be having here 80 by 3 into cos theta plus you will be having here 2 cube, 32 by 3 into sin theta plus you will be having just 3 to 6 here, 6 d theta. Okay, so all of this within the limit 0 to 2 pi, so you will be having this is equal to 80 by 3 sin theta within the limits 0 to 2 pi plus 32 by 3 into minus cos theta within the limits 0 to 2 pi plus 6 into theta within the limits 0 to 2 pi. Now these terms will be 0, right? Because we are integrating it over an interval 0 to 2 pi, and you know sin theta is periodic with period 2 pi. So here you will be having 6 into 2 pi. So the final answer is 12 pi. And when we evaluated it directly, there also we got the final answer is 12 pi. So we can conclude, hence LHS equal to RHS, hence verified. So we have verified the Stokes theorem here. Okay, thank you.